Okay, we'll continue our discussion on elasticity. We've spoken about elasticity and plasticity. Our ability to return to the original shape is elasticity. When it cannot return, then it is said to be plastic. But now I want to move on and just use the laws that are involved. And the first one is Hooke's law. This states that as long as you don't exceed the elastic limit, the force is directly proportional to the extension. I just summarized it, but those are the key points. The main thing is provided, as some will say, provided the elastic limit of a material is not exceeded, the applied force is directly proportional to the extension. That is Hooke's law. And so you just have F, which is force, is proportional to extension, which is E. Again, remember the condition. You do not exceed the elastic limits. We spoke about it before. Once you exceed the elastic limits, it has become plastic. And Hooke's law applies only to elastic materials. As usual in mathematics, when you have the sign of proportionality, you cannot solve. So in taking it out, you introduce a constant to bring in your equal to. So you have F equals KE. Where F is your force, you have to note this is physics, so you must always deal with SI units. So your force has to be in newtons. K is referred to as the force constant. And in this case, it is Newton per meters. And then your extension is your final length minus the initial length. But the most important thing, it has to be in meters. You use your SI units. So if it was in centimeters, that's your extension, you have to convert it to meters. You divide by 100. If it's in millimeters, you have to convert to meters. You divide by 1000. You remember the popular saying, 10 millimeters makes 1 centimeter, and so on and so forth. But the most important one that we need here is 1000 millimeters makes 1 meter, and 100 centimeters makes 1 meter. So if you are converting from centimeter to meter, you divide by 100. If you are converting from millimeters to meter, you divide by 1000. You have to follow your SI units. So the force on any elastic body is given by F equals KE. You may be told the kind of elastic body. You may not be told an elastic material per se. You may be told a spring. You may be told a rubber band. Just trying to use examples. So you don't have to be told an elastic body totally. A spring is elastic, so automatically you're talking about Hooke's law. A rubber band is elastic, so automatically you're talking about Hooke's law. But if they tell you elastic material, fine and good, you go on with it. So from here, it can go either way. You know F equals KE. So if you are looking for K equals, you divide both sides by E. K equals F over E. So that is for the force applied on an elastic material. Now the next one is, what about work done? Work done, as we know before, work done has always been and will always be force times distance. That's exactly what it is. Force times distance. But remember, the distance you move now is not distance like along a road or something. The distance you move is from the initial length to a new length, and that you call the extension. So therefore, distance is actually equal to E, because the distance is the extension. Distance is it moved from a particular point to another point. And in an elastic material, the initial point is your initial length, the final point is your final length. The difference between those two is your extension. So in elastic materials, your distance is the same as your extension. However, in applying the force, you have to look for what is called the average force, which is basically the initial force and the final force divided by 2. So let's call it F1 plus F2 divided by 2. But in all this case, this is now referred to as F over 2. So now, what happens next is you now know your force is half F. You know your distance is E. So automatically, your work done becomes, your force is half F and your D is E. So you simply, work is force times distance, but your force is half F and your distance is E. So this, it becomes force times distance. That is half Fe. And that is the formula for work done in an elastic body. However, what if you are given the force constant instead of the actual force? You can also maneuver your way through it. Why? You have known that F equals KE. So you can go in 2 steps. Some people go in 2 steps. What they do is, imagine you are given K. So what happens? You have to remember that F equals KE. So what somebody can do is solve for F equals KE first. That gives you your F. Then you substitute it into work done and get your work done. Or somebody can say, no, let's combine the 2 processes. So work done becomes half. Remember, F equals KE. So you take out F and you have KE times the other E from extension. So you now have half KE squared. So your formula for work done is, you are using half Fe, or you can use half Ke squared. Those are your 3 important formulas. F equals Ke, that is the force applied. Half Fe, that is the work done, or half Ke squared, also the work done. But it all depends. You can see in case 1, you are given the force. In case 2, you are not given the force, you are given the force constant. Up next, we discuss Young modulus. Elasticity is simple. These are just the formulas involved. Now, what is Young modulus? Young modulus simply says that the ratio of stress to strain is constant. So literally, most persons, when they define Young modulus, they just say stress over strain. And that is all. But if you want to put a story, Young modulus says the ratio of stress to strain is constant. Some add the fact and they say tensile strength to tensile strain is constant. Your choice. Now, what is stress? Stress is like the amount of pressure exerted on something. So stress is referring to pressure. And if you remember, pressure is force over area. And then strain means by what ratio did you stretch it? So strain is extension divided by the initial length. So therefore, your Young modulus represents as not really Y, but I guess you can use Y. Stress over strain, that is F over A. That is stress divided by E over L. Now, if you observe this one, following dimensional analysis, force is Newton, area is meter square. So the unit to be Newton per meter square, just like pressure. But if you check out the dimensional analysis of this, Extension is in meters. Length is in meters. Meters cancel meters. So you hear the fact that strain has no dimension. So if you are following for Young modulus, automatically the unit for Young modulus, oh, I said dimension, sorry, has no units. So if you are following Young modulus, the unit for Young modulus has to be newtons per meter squared too. So you can go on from here, but I suggest if you want to solve, if you're looking for Young modulus, force over area, solve that, then extension over length, solve that. But you may be in cases where you are given the Young modulus and you have to calculate any of all the others. So let's see, what do we do? This is force over area divided by extension over length. When you have divide, you can't solve, you turn it upside down. So you have force over area times length over extension. So automatically Young modulus becomes force times length divided by area times extension. So you cannot use this. If you are given the Young modulus, maybe you are asked to look for the applied force, you are asked to look for the initial length, you are asked to look for the area, or you are asked to look for the extension. Then this becomes easier. Anyone you choose to use, it is the same thing. Just be able to remember, Young modulus is stress over strain. Stress is force over area, and strain is extension over length. So you can see, those are the formulas that you need. Formula for applied force, F equals KE. For work done, there are two. So I'm going to use a table, something like this. The first one is half FE, and the next one is half KE squared. And then we have for Young modulus, which we have derived, and we have gotten FL over AE. So with these formulas, you are good to go in any question that comes when you are asked with regard to an elastic material. Like I always say, in physics, the most important things are the formulas. So what you just do, all these formulas, note them down somewhere, so you can always make reference to them. And once you're able to do that, you are good to go in your physics. So now, let us look at one question. This question says, a spring 20 cm long is stretched to 25 cm by a load of 50 newtons. What will be the length when the load is stretched by 100 newtons? Oh, let me shorten it. What is the length when stretched by 100 newtons? So I guess you may say, again, the condition, the elastic limit is not reached. If the elastic limit is reached, then automatically you have broken it up. And we are going to be looking at questions later that involves a force extension time graph, where you have to calculate the area of the shape on that in question. But for now, let's focus on this. The string was stretched. It was initially 20, but it was stretched to 25. So what does that tell you? You are talking about extension. And it was stretched by a load of 50 newtons. So you are dealing with force and extension. It is just that clear. So now what do we have? We have that force equals KE. Now I'm going to show you a simple way to solve this, because what you are doing is you are comparing two situations. And remember, K is a constant. That means K has to always be constant. I'll show you the first method, and then we'll go over to the second method. The first method I believe is shorter that we can use. So let's call this method 1, and over here we are going to have method 2. The choice will be left for you. So now, the first point here is, no matter what happens, you are dealing with 2 loads, you want to look for the next extension. The point about K is that K is always constant. And we have already seen earlier that K equals F over E. K is a constant, that means it does not change. So that means that F1 over E1 must be equal to F2 over E2. It is always constant. That's why it is even called force constant. So let us see. What's our F1? F1 is 50 newtons. That's the first force we are given. E1, remember, your extension has to be in meters. But first thing first, let us get the extension. What is the extension? The final length, it was stretched to 25, minus the initial length, it was initially 20, which is 5 cm. But remember, it has to be in meters, so it will be 5 divided by 100, which will be 0.05. That is E1. What's your F2? Your F2 is 100 newtons. This is not meters. And your E2 is what? You don't know. You are looking for the length, not the extension anyways. But what happens? How do you know the new length? The new length has to be the initial length plus the amount by which it extended. All right. So now we can go on. F1 is 50. E1 0.05 equals F2 100 divided by E2. From there, simply cross multiply. Now, obviously, you know 50 will multiply E2, and you're looking for E2. So you are going to have to divide both sides by E2 later. But let's follow steps. 50 E2 will be equal to 100 times 0.05. And then E2 equals 100 times 0.05 divided by 50. So when you do this, 50 divided by 100 is 2. 2 times 0.05 should give us 0.1. So 0.1 meters. When you convert back to centimeters, I guess we could have solved it earlier in centimeters. But I want to show you, in this case, if you solve it in centimeters, you have no issues. But I want to show you that when solving, you have to always convert to meters. In this case, it has no issues, but in other cases, it may have issue. Converting meters to centimeters, you multiply by 100. So that gives you 10 centimeters. So automatically, they ask for the length. What is now the length? Length is the initial length plus the extension. The initial length was 20. The extension is 10. So the new length now has to be 30 centimeters. And another way you could have gotten it, observe, your extension is 5 centimeters. The load was doubled from 50 to 100. The load was doubled, so the extension is also going to double. So the extension is going to be 10 centimeters, like we got. So your new length will just be the initial length, which was 20, plus the extension, which was 10. Those are ways you can observe such things. Now, what about method 2? Method 2 is you don't want to use this. Oh, the ratio is always constant. Method 2 is you want to go step by step. Well, there are no issues with that. All you simply have to do is start with the first one. We have gotten the details, so I'm not going to go over that again. So the first one is from F equals KE, you need the constant from the very first situation where the load extended it. So K equals F over E. And the F in that case was 50 divided by the extension, which was, like I said, we want to solve in centimeter now because our final answer is going to go back to centimeters, which is 5. So our K is now 10 Newton per meters. So this K is always constant. We move it over to the second situation. Now, what is the length if it was stretched by 100 Newton load? So you have to look for the extension. So F equals KE. We are looking for extension now. That means E equals F over K. So you deal with situation 1, then you go to situation 2. Now, what's our E? We are looking for it. The F now is the second situation. The F is now 100 Newton load that was applied, divided by our K, we got it as 10. So our extension is 10 centimeters, exactly what we got. So our length now, if I said extension, you stop here, but they said look for length. Is the initial length plus the extension, which is 20 plus 10, and that is 30 centimeters. So it is just that clean, clear, and straightforward. Alright, so we'll be looking at more examples. But you can try some examples, and if you have some questions, and if you have issues, let me know. We start with those questions in our next video.